based on your today I'm just going to show you. Today I'm just going to show you how you can potential chemistry, molecular hexacarbonyl, tungsten hexacarbonyl. You have studied a lot of metal hexacarbonyl. You have studied a lot of metal carbonyl complexes. Okay, but there are not many examples are not there for many group with that carbon monoxide. Okay, so that's what we are going to see here. Okay, so. So, for example, N2O, carbon monoxide or carbon dioxide. So, these are the waste emissions in many processes. Okay. So, for example, these waste emissions, so we can react with the main group compounds. So, we can convert them into value-added products. Okay. Value-added products means they can be used in either material industry or they can be used in agrochemical or you can be used them in the pharmaceutical industry. So, these are the waste emissions. So, if the waste emission gas can be reacting with your low-valent compounds. So they can form some value-added products. Value means so they have some value. For example, it can form formic acid or acetic acid from carbon dioxide. So they have some value in the industry. Okay, so that is called value-added. From waste to we are making value-added. Okay, so those are the important things. So these, for example, N2O, carbon monoxide or dihydrogen. So this is their bond dissociation energy. So you need to give this much amount of energy to break the bond. Okay, so that's what very important. So a lot of examples known with the transistor metal chemistry, but there are not many examples known with the main group chemistry. Okay. So this is the one example I have shown you previously. This is magnesium in +1 oxidation state. Okay. So we try to react with carbon monoxide to see whether it can react or whether it can break the bond. But no reaction happen at different temperature, pressure. No reaction can happen. Okay. So this is previously reported example. This is my postdoctoral work which I have done in Australia. So previously, these examples are reported. Donor, okay, D means either DMAP. Maybe I'll show you. This is the DMAP. So this is kind of a Lewis base. Okay. So this Lewis base can donate this electron to the magnesium. Then the magnesium bond distance will increase. Okay. For example, here the magnesium bond distance is around 2.8. When you put two donors, either DMAP or DHF, the bond length will be increased. Then it will come close to 3 angstrom. Okay. So this work already done. So when I went there, so I thought instead of using DMAP, N-nitrocyclic carbene, I know they have got a sigma donor and pi, etc. So I thought, can I try with the same reaction? So when I tried the reaction, instead of two, only one carbene is coordinating to one of the magnesium center. Actually, I have used two equivalents. So I expected to form same, but it is only one carbene is coordinated. Okay. So maybe the steric is due to the steric reason, maybe another difficult for another carbene to come and coordinate. Okay. That is one example. These are the crystal structures. I have told you once you synthesize, we will do NMR, then we will calculate the single crystal XRD. So you can see here, this is the structure, okay, structure of the compound. For example, sodium hydroxide, you are writing methane, ethane, benzene, right? So how you are writing? So it's not characterized by either spectroscopic technique. Similarly, whatever the compounds we make, so we have to calculate them by single crystal XRD as well as NMR spectroscopic. We need to use some NMR technique. Okay. So you can see here one of the magnesium is 3 connections, 1, 2, 3, and another magnesium is 4 coordinated, 1, 2, 3, and you have one more. So you have 1, 2, 3. So one of the center carbon is coordinating. So that's what makes different reactivity. Okay. So I will not discuss this detail. Okay. I move on to the next slide. Okay. So what we did? So we took one of the magnesium bonded. So I will call this as 1 to 1 array because. So in one of the center carbon is coordinating, and you have one side 3 coordinated, another side 4 coordinated magnesium is there. So we have reacted with carbon monoxide. So what you see here, you can see here 3 carbon monoxides are coupled together. Okay. So for example here, you can see the difference. So this bond has been broken. So you can see here, this is 1, 2, 3. 3 carbons are there. You have 3 oxygens are there. So 3 carbon monoxide coupled together to form this species. Okay. And this is another study. We have also tried instead of 3, you can see here 2 carbon monoxides are coupled to form another species. Okay, so this is called deltate, this is called ethane dialyte. Okay, no need to remember the name, maybe it is difficult for you, but what you can see here. So, for example, here, if you look at this example, you have this group. For example, xylene, you have 1 methyl, 2 methyl. If you look at here, you have isopropyl group here. Okay, so you have isopropyl group here. So if you have a methyl, it is reacting with 2 molecules of carbon monoxide. If you have isopropyl, with 3 molecules of carbon monoxide. Because small change in the steric, okay, the reactivity is completely different. Okay, so that's what I'm trying to say here. This is another example where magnesium reacted with carbon monoxide. It reacted with 6 molecules of carbon monoxide. For example, if you put OH here, this is called benzene hexol, right? So this is your benzene structure. Then you have 6 OH. So from carbon monoxide you can form these molecules. This is what I'm talking about, value added products. Okay, so this is what I'm talking about, value added products. So this is the crystal structure of this compound. So see, no one will believe if I draw this structure until I get this, structural information. So previously we have seen magnesium reacts with either 3 molecules of carbon monoxide or 2 molecules of carbon monoxide. Here, instead of Lewis base, we have used molybdenum hexacarbonate. So that's why this reaction lead to the formation of different products. Okay. So this is another example. Okay. So where 4 molecules of carbon monoxide are coupled together to form a squarate. Okay, this is called a squarate molecule because we have 4 molecules of carbon monoxide are coupled. So here what we did, we combined the first strategy as well as the second strategy. That means the first strategy we reacted only with the Lewis base. That time we formed either with the molybdenum hexacarbonate. That time 6 molecules of carbon monoxide were coupled. So currently we combine both the strategies, so we could form 4 molecules of carbon monoxide are coupled to form this squarate species. You can see here this is the crystal structure. And you can see here, this is the magnesium, this is another magnesium, bridging between these 2 squarate units. Other 2 magnesium centers are chelating this each squarate unit. Okay, so without crystal structure, no one will believe. So we have got crystal structure for this compound. So this is one of my.
I'm sorry to interrupt you. In the previous slide, you've shown CO.
Yeah.
It's a solvent, 4 times of CO. Is it a solvent or what?
No, CO is a gas molecule, right?
So taking gas in state of 80 degrees Celsius something.
No. So how do you do your reaction? So you will have a closed system. Suppose you may know autoclave, right? So for example, if you take this magnesium 1 compound, you take this molybdenum hexacarbonate, you can put it in your reaction vessel, you can add your solvent. Then you already have some gas inside your headspace, so you need to remove the gas. Then you need to put the carbon monoxide gas inside.
You degassed and you inserted carbon monoxide.
Yes.
The role of the carbon monoxide is the role of the solvent or something else.
No, it's a reactant. It's not a solvent, right? Solvent will not react, right? So this is as one of the reactants. So that's why it is reactant. Solvent role is not a reactant for our product.
Sorry to interrupt you. Last doubt. Therefore, heating to around 80 degrees Celsius, still we are ended with 4. The cycle size is 4. So yeah. The molecule stability remains question.
No. So this molecule is thermodynamically stable. That's why this is forming this product. Previously, you have seen it formed different products. So what I'm trying to say here, so if you change your strategy, so you may be able to form a different product. So that's what I'm trying to say. But here, carbon monoxide is not a solvent. It is used as a reagent. So for example, it is one of the reactants. So it reacted with this product. Okay, this is the product. So there is carbon monoxide is not a solvent. It's one of the reactants.
Non-break work it is.
Yeah, that's why they all got published in very good journals. So actually, this what many people tried before. So there was only one change we did. So we changed this, with the carbon that all the reactivity has been done. So when I went, my professor told this what we have already proposed, but we have tried it. We are not successful for so many years. So then he told, you give up on this project, we will try to do a new project. So then I was so interested, then I was trying somehow, when we change the substituents, so this carbon is very important. In the previous case, you have here one donor, here one donor. So both are having 4 coordinated, but here one side is 3 coordinated, another side is 4 coordinated. So then the magnesium bond also polarized because here is delta positive, here is delta negative. For example, in the carbon acetone, you have delta positive, delta negative charge. Similarly, there is a difference in the electron density of these 2 magnesium centers. So that is the main reason to undergo all these different reactions. Thank you for that question. So in summary, okay, so we could able to form 2 coordinate react with 2 molecules of carbon monoxide. Now we could selectively react with 3 molecules of carbon monoxide. So we can also selectively react with 4 molecules of carbon monoxide. In the end, we could show that it reacted 6 molecules of carbon monoxide to form carbon monoxide into some of the it converted into RE species. Okay, so So next I'll go on to my research work which I'm currently doing at IIT Palakkad. So I'm sure you have seen what is this, right? Have you seen what is this? It's a glow stick. Probably have seen, or probably have used glow sticks. Okay. So this is some of the compounds. They are highly fluorescent or luminescent. Okay. So this luminescent compound has a lot of applications in bioimaging as well as OLED applications. That is, it means organic light emitting diode. Okay. So for example, these are the only reported examples. So my most of the work in postdoc was magnesium. So I got to continue the same, but I don't want to do the same work. But I have observed only 3 examples are known. So these examples shows luminescent properties. Okay, so I thought to continue, but I want to change the ligand system. Okay, so that's why I have chosen this different ligand system. Okay, so for example, this is called phenothiazine. So if you take phenothiazine, you react with a magnesium precursor, you will form homoleptic. Homoleptic means with the metal you have 2 same ligands. So this is another example heteroleptic. So you have metal, you have one ligand, you have another different ligand. Okay. So our aim is to make magnesium complexes with different ligand system. So phenothiazine molecules shows a lot of photophysical properties. So we have made homoleptic compounds as well as this is crystal structure. So here magnesium is co-coordinated and the magnesium is bonded. This is another example. Okay. So similarly, we have also made heteroleptic compounds. For example, here you have different ligand system. So previously magnesium is bonded to this ligand system, this side as well as this side, but now you have 2 different ligand systems. Okay. So this is how the compound looks like, but when you shine a light, like shine light means you have to shine a UV light. So when you shine a UV light, this compound also shows very good fluorescence. Okay. So this work is in progress. So we will try to make publish sometime soon. Okay, again, this is I told you, whatever you make, so you need to have evidence that you made the compound. So the crystal structure is one of the strong evidence that you are able to make this compound. So this is a crystal structure of the heteroleptic compounds, whatever we made. Okay. So another important thing, other than fluorescence, we are also interested to do the 3 bond activation, because carbon fluorine bond is one of the strongest bonds. It is difficult to break. Okay. For example, when we reacted our heteroleptic compounds with this fluorinated nitro compounds, you can see here this fluorine is substituted by this nitrogen compound, so we could able to undergo the C bond activation. Okay, so this is one example. We have also created 2 substrates where you have only 1 fluorine and you have either 2 or you have 3 fluorines with this nitro compound. In all the cases, our compound able to substitute the fluorine with the corresponding this amide group. Okay, so usually this reaction is done in the presence of palladium. So palladium they use as a catalyst. So this is very expensive. Palladium metal is very expensive. Even nowadays it's difficult to get the palladium. So we showed that by using a simple magnesium is very cheap. So palladium 1 gram probably 20,000. Even 500 gram you can buy maybe 2,000 rupees maximum this magnesium metal. So you can buy very cheap. So that's why we could able to show them as a catalyst. So these are the different arenes. So previously there is a nitro is there, so those arenes are activated. So here you can see here. So this is a simple arene. So this also could able to undergo CF bond activation. Okay, so this is some of our recent results. This is the last example I'll show you here. So similarly we have made some of the interesting ligand system you can see here. So we have also made the boron compounds. So this boron compound also you can shows a very important fluorescent property. Okay. So in conclusion, okay, so much main group chemistry has been done over the 5 to 6 decades. So I have just shown you all of them, and also I told you how it is important. So your ligand is very important. Ligand plays very important role in isolating these global and main group compounds. Also you can able to isolate multiple bonds, anions and cations. Okay, then the latest slide I have showed you how magnesium 1 dimer can react with carbon monoxide. Also it can form various oligomerization products. In the end, I have showed you that we have synthesized some homoleptic and heteroleptic magnesium compounds. Among them, heteroleptic complexes shows a bright green luminescence. Also, we further showed that this compound has been used as used for CF bond activation for various aromatic compounds. Okay, so moving forward, so main group chemistry will continue and flourish in the future. Okay, so just 1 or 2 slides about IIT Palakkad. Okay, so IIT Palakkad is established in 2015. So it's almost 10 or 11 years ago. So you can see here, so this is the Western Ghats. So our campus is right behind the Western Ghats. Okay. So still some of the construction work is going on. Probably in 5 years, we will have a big campus. So we have 11 departments, okay, and we have around 140 faculties, and we have around 1,500 students. Probably in 5 years, this number will be doubled. So we will have around 300 faculties, probably 250 staffs, around 3,000 to 4,000 students will be there. So in chemistry department, we have 14 faculties. So we are working in experimental as well as theory, various innovative topics. Currently, we are working. Okay. So if you there is no BTech student here, so mostly you are MSc and MTech. So if you clear your exam, probably you can do your MSc at not only in IIT Palakkad, you can do in any of the IIT. So I will strongly request all of you to clear exam. Okay, so exam is important. If you clear exam, you can easily go to any IIT. So that will really help your career. Okay, and if you want to do PhD, if you are qualified CSA or GATE or Express Fellow, so you can apply to the IIT, so you can get a chance to do your PhD. Okay. So finally, my acknowledgement. Okay, so this is my research group. So I have currently 4 PhD students are working. This is my PhD supervisor, Professor Sundar Gopal Ghosh. This is my postdoctoral supervisor, Professor Cameron Jones. Okay, so these are the various funding agents. IIT Palakkad, I thank for IIT Palakkad, and I got some projects from SCRT, so I thank to SCRT as well. So I thank to Manas, IIT Madras, and Australian Center of Courses. And I know, Elias Desupakian. Okay, so he's a undergraduate student. Did studied in St. Xavier's College, and probably then he came to St. Joseph College for his master's. So he was my senior. So he really helped me in many ways. So I have never met him. So when I joined, so he completed his master's. Okay, during the convocation he came to our institute. So then I had an interaction with him. Still now I talk to him. He even helps me a lot. And he's one of the person, during my PhD. So he helped me to join with Professor Sundar Gopal Ghosh. So that time, I came from very village background. I have very limited exposure. So that time he told me that he will be a really good professor. We can work with him. So I really thank to him, for his support. Okay. So thank you all. I'm happy to take any questions. So don't worry, maybe some of the topic you may not able to understand, but what I'm showing here. So there are many things which you may not aware of. So I don't want to teach what you already know. For example, coordination chemistry or molecular theory or organometallic catalysis. So you all know. So I don't want to teach. So I just want to show you some exposure. So that's why I'm trying to show something different which we don't know. Okay. Thank you.
Any questions? Sir, your lecture was really very interesting. I could understand from your things for the first time from a person from IIT.
But you told me that last time when you were a student you are not able to understand. But it's interesting to know that.
But our students' education is genetically stable and thermodynamically stable.
It happens, but it's all up to students. So you have to spend a lot of time. So it's very important to clear CSIR exam or GATE exam. Then if you go to PhD for the good institute, then your life will be good. Okay, otherwise it will be difficult to shine in the light.
Because all night they will study, the next day they write, the next day they will forget. Because the semester pattern of education is installment studying and installment forgetting. Everything goes on. So more dynamically stable education, we have to have reversibly. The learning process should have infinite number of steps, and each step should be infinitesimally slow. Thermodynamically stable education. So when Sar was speaking, he spoke about this sodium metal. When it is put in water, you can observe a very vigorous reaction, forming sodium hydroxide and the liberated hydrogen, and the liberated hydrogen will immediately catch fire.
Even potassium is dangerous.
Potassium is also. But if you put the sodium chloride or potassium chloride into water, nothing will happen. The difference is in metallic state, the sodium is in the zero oxidation state. In sodium chloride, it is in the +1 oxidation state. The presence or absence of one small electron makes all the difference in the reactivity. Similarly, presence or absence of enthusiasm will make all the difference in your life. So enthusiastically participate in the seminar I think you might have not seen that big hit found in the St. Joseph's College laboratory by the explosion of 8 kilogram of sodium. You have not seen it. Yes. In St. Joseph's College, they stored 8 kilogram of the sodium in the underground. It happened in the year November 1977, the highest flood level in St. Joseph's College. You can go there, you can see a mark. HFL 21/11/1977, which means that the highest flood level 21/11/1977. At that time, the sodium pot it floated and got inverted, and all the kerosene came out, and the sodium got exposed to the flood water. And there was a very big explosion. Even today, the very big pit is being maintained to show that it is because of the explosion of the sodium. Sodium will react. So if you have enthusiasm, you will also react. And also if you study thermodynamically, reversibly, you will also become great person. Sir, if I come to IIT Palakandi, just admit me as a postdoc.
Yeah, great pleasure to welcome you there. But if anything possibility, I'll definitely.
Yes, please.
Definitely get back to you. But really very interesting speech, how to connect the chemistry in the class as well as with the subject. So I really like your speech.
Thank you, sir. Thank you very much. Thank you. And today's part has mostly concentrated on the catalysis. Catalysis, no. What is a catalyst? What's a catalyst? The substance which alters the rate of the reaction and remains unchanged after the completion of the reaction or at equilibrium in its mass and the chemical composition. So the definition should have all the pieces of information. Every no more question should come, which alters the rate of the reaction. Sometimes increases, sometimes decreases. So it alters and it remains unchanged. When? Not during the reaction. After the completion of the reaction. All reactions will not attain the state of completion, because reversible reaction will attain equilibrium or at equilibrium in mass and the chemical composition, quantitatively and qualitatively catalyst will not change. Today professor has come here, qualitatively, quantitatively it has not changed, but he has come and accelerated the process of learning in you. Is that right? His presence has accelerated the process of learning in you. And I'm very sure, sir, your presence accelerated the learning process. God bless you. Thank you very much.
Thank you, sir, for recommending on the learning. Thank you, sir. And also I thank Dr. M.S. Selvan for inspiring the speech. Now we will have a short break. Kindly reassemble.
See, please note that there are a few announcements. So the announcement one is for offline oral presentation, kindly assemble room number 32. Room number 32. The staff in charges will guide you. Right? Offline oral presentation, room number 32. And for room, the announcement 2 is regarding the poster presentation, offline poster presentation. Kindly place your poster just outside the Counselor Hall, the veranda. Yeah. In veranda you can place the offline posters. And announcement 3 is please sign the registration form. Right? Please sign the registration form. When you come here, most of the people will sign the registration form. So please sign the registration form. I think all should sign the registration form. And 4th is, now we have a short tea break. Tea is available outside the Council Hall. You can have tea and kindly reassemble at 11:30 a.m. kindly reassemble here at 11:30 a.m. Now let's discuss.
ஜூம் எதில் கிரியேட் பண்ணா ஜூம் லிங்க்கு அது அவர் தான் கிரியேட் பண்ணி கொடுத்தாரு.